Okay, so I think we can start. I just will want to say a few words before we start with the first speaker. So welcome everyone at this third and last day at this SIP SAZERAC meeting on learning the high-redshift universe. So just a few information, especially to the speaker. I would like to remind her that if you want, you can upload your slides on the Google Drive to share with the other view. And to feel welcome to make question to the viewer on these on the actual dedicated channel on the SAZERAC Slack group. So today we have two more sessions. The first one completely with a total of 4 talk, and then we have a second session with some more talk and a final discussion by Isabella Carducci and Stephen Murphy. So I also wanted to mention that there is an upcoming SAZERAC meeting in March, between the 14th and the 17th March, and the submission are at the moment not yet open, but are open until the 14th February, so next week in 10 days. So feel free to go to the SAZERAC website and look at the description of this meeting. So with no further ado, I stop sharing my screen and I give the floor to Ivan Nikolic from Scuola Normale Pisa. I hope I say it correctly. That will talk about inferior ionization and galaxy property from the Apache kinetic Sunni ZWH signal.
Okay. So hi, everyone. My name is Ivan. I'm a second-year PhD student from Scuola Normale, and I'm going to talk about what we can learn from the Apache kinetic Sunni ZWH signal. So the epoch we're interested in this work is the Epoch of Reionization. However, there were some talks before me who introduced the topic and talk by Charlotte Mason, so I won't go into too much details about the Epoch of Reionization. I'll just say that the uncertainties we still have about this epoch are great, and we don't have that one observation that's able to cover it, and that's the situation until the 21 centimeter cosmology kicks in. And until then, what we have to do is we need to combine different observations. So for example, we have the Lyman alpha forest in quasar spectra for redshifts higher than 5.7. This way we probe the end of the reionization, and it looks like the data points to a late end of the reionization. We also have the UV luminosity function, so we heard some talks about that. So we are still missing the faint end of the UV luminosity functions, but still we can put some constraints on the sources that contribute to the reionization. And of course, we have the CMB optical depth to reionization. Here I'm quoting the value from Planck 2018 paper. By the temperature and the polarization spectrum, we get this value. And with this, we can probe the extent of the reionization. However, this is not the only probe of the reionization we have from the CMB. And we can learn something about the reionization also from the kinetic Sunni ZWH signal. So as CMB photons travel through the universe, they can scatter with the electrons that are set free during the reionization. And this creates a secondary anisotropy in the CMB spectrum. And this is schematically shown on the right and on this equation on the left. And this scattering depends on the details of the reionization. And this signal we can separate into two components. The first one is the patchy one. So during the reionization, as CMB photons scatter, the fluctuations in the ionized fraction create boost the power spectrum. However, after the reionization, this term in red is pretty much homogeneous, and we have the fluctuations in the density. And these two components are summed up in this line of sight integral. So what we measure when we measure the kinetics near-the signal is the sum of those two signals. But it's the patchy KZ signal that's a probe of the reionization, and its power spectrum depends on the morphology and the duration of reionization. So yeah, needless to say, there is a large cosmological effort to measure the signal. And recently there was a measurement by the South Pole Telescope collaboration, who placed a measurement of the power spectrum at a multiple of 3000. And then using the modeling of the homogeneous post-reionization KZ signal, they managed to put constraints on the patchy KZ signal. So I'm marking here the value of it. So, okay, now we have the measurement of the signal. What we need to do in this work is to model this patchy KZ signal. So for that, we use the 21 centimeter fast code, which is publicly available. It provides us with light cones, such as the one in the upper panel. So this is the light cone of the neutral hydrogen fraction. And using the equation I've shown before, we can model the signal. So for a given reionization history and for a given astrophysics, this is shown in the panel on the left, and the power spectrum of this map is shown on the right, along with the measurement. So okay, now that we have the measurement and we have the modeling, what we want to do is to put constraints on the astrophysics of reionization, to put constraints on the reionization itself, using this one number. So in order to do that, we need to parameterize our astrophysics, our galaxy modeling. So we do that with 6 parameters shown here by red, in red. And so, yeah, let me lead you through that. The stellar barrier fraction we model as a power law in halo mass with a normalization at 10 to the power of 10 solar mass. Then we have the UV luminosity, which is proportional to the star formation rate, which we parameterize with this T, which is a standard time scale for star formation. Then the output, the ionizing output, is proportional to the escape fraction, of course, which we model as a power law in halo mass again, with normalization again at 10 to the power of 10 halo mass. And we also implement a duty cycle to suppress star formation for low mass halos due to various feedback mechanisms. So these 6 parameters are our parameter space that we are trying to constrain with observations. And there were previous works that did that. For example, Yu Shengjin's paper from last year used Lyman alpha forest data, CMB optical depth, and UV luminosity functions to put meaningful constraints on this parameter space using the 21 CMMC code. And so the idea behind this work is to use this distribution as a sort of a prior and to see what the addition of the KC likelihood, so using the modeling that I've shown before, how can we modify this parameter distribution? What can we learn, and how does it change with the addition of the KZ likelihood? And also, what is then our total knowledge of the astrophysics of reionization? So to do that, we use the multi-nest sampler, and it is shown here in this video how it works. So we start from a set of live points here marked with black points that cover the parameter space, and at each iteration we select a point which has the lowest likelihood times prior, here marked with green. We remove it. We remove it and we take another point with a higher likelihood times prior, and this way we squeeze our space that our live points in which our live points are, and then we move to the points with the highest likelihood times prior, the probability, the posterior. And so this is shown by this red contour. and it is better shown in the next slide. So with blue, I'm again marking the distribution I've shown before from Yu-Sheng Jin's paper. And with red, I'm marking the posterior after the addition of the KSE likelihood. So as you can see, for some parameters, we are reproducing the parameter constraints from before, but
5 minutes left.
Yeah, for some parameters such as the alpha escape and the F escape, we have some change. For this is more notably seen in this second peak here. So it looks like our patchy KZ signal prefers larger halos to ionize the universe, to contribute to Reionization, because alpha escape, they have the biggest escape fraction. And this was already seen in the previous data. So this second peak was it was commented that it was because of the Lyman alpha forest data, which also prefers larger alpha escape, meaning larger halos that dominate the ionizing output. And this term means that we have a latent rapid end of the reionization. And this first peak is from the CMB optical depth measurement. So our patchy KZ is in line, we can say, with the Lyman alpha forest data. This is more clearly seen when we look at the distribution of EoR histories. So red curve is again our posterior after the addition of the KZ likelihood. We see a latent rapid end to the reionization is preferred. And of course, our amplitude of the signal is shifting towards the measurement when we had the KZ likelihood. So the next step, which I hope I'll talk about in some next talk, is what future measurements will tell us about our parameters. What are the future constraints we can get? So we expect in the future that a factor of 10 reduced error bars, and now we are running our sampler again with reduced error bars to see what a sort of a forecast what we will learn in the future KSZ measurements. And with that, I would like to summarize and say that our patchy KSZ signal measurement points to a latent rapid end of reionization, which is in line with previous Lyman alpha forest data, and that future measurements will hopefully put further constraints. And with that, I'll end the talk and take questions here or on Slack. Thank you.
Thank you, Ivan. So I quickly look into the participant. If there is some raised hand, feel free to make question on the Slack channel. I see Gareth, you have hand raised. You can speak up.
For reionization, but especially for the KAZ, to get a good representation of the velocity field, you need to have you need to simulate quite a large volume. So what is your volume size that you're simulating in this in your work?
Yeah, I've shown in the first panel that we simulated with so we need 1.5 gigaparsec to accurately simulate the velocity field. That's correct. But unfortunately, with the sampler, this is unfeasible to put such large for each iteration to simulate such large volumes. So instead, what we did, we developed a scaling relation to scale our power spectrum when we use smaller volumes, so that we can replicate the large volume power spectra. But yeah, it's a good question, because this is the huge limitation that we really need to large volumes to be very accurate about the KZ. Yeah.
Okay, thank you.
I think we have to move to the next speaker, but feel free to ask Ivan more questions on the Slack channel. Thank you again, Ivan. So next speaker is, Florent Mertens from LERMA, Paris Observatory, and we'll talk about some machine learning enhanced foreground mitigation method for 21 centimeter experiment. Florent, the floor is yours.
Yes, thank you, and hi everyone. So I am Florent Mertens from the LERMA, and today I would like to talk about ML-enhanced foreground mitigation method for 21 centimeter experiments. This is a work I've been doing in collaboration with Jérôme Bobin and Isabella Carucci. So our aim is to observe the 21 centimeter signal from the cosmic dawn and Epoch of Reionisation, which will allow us to shed lights into the first billion years of the history of our universe, to investigate the properties of the first stellar population, as well as the source that drives the reionization, and to observe the fluctuation of this signal at different redshift. We use radio interferometers like LOFAR, NUFAR, and in the future SKA. But this is a very challenging experiment, and indeed the signal we try to detect is very faint, and we need to disentangle it from the foreground emission coming from our extragalactic source and our own galaxy, which are order of magnitude brighter. And at the radio frequency we are observing, we are also affected by the ionosphere and radio frequency interferences. And we can also have systematics coming from our own instrument. And so all this effect needs to be corrected or mitigated as much as possible in order to be able to observe this 21 centimeter signal. And one of the biggest challenges here that we face are the foregrounds, which are, as you see here, order of magnitude brighter compared to the 21 centimeter signal. But there is a way to separate them. And indeed, the 21 centimeter signal is expected to be uncorrelated on a scale of megahertz, while the galactic and extragalactic foregrounds are mainly synchrotron and free emission, which are frequency coherent. And so in the spatial versus frequency or line of sight power spectra, they occupy a different space. However, when you add the fact that we are using a chromatic instrument, both in primary beam and UV coverage, that you have the effect of the ionosphere, that you have residual calibration error, all this will scatter the otherwise smooth foreground to higher line of sight modes into what we call the foreground wedge. And this has a big impact on the the big impact that it has is that the foregrounds dominate at a large scale, where the instrument is also the most sensitive. And so avoiding the foreground by discarding the wedge mode can have a severe impact for an experiment like LOFAR and even for SK. So in this plot here, what I'm showing you is the sensitivity of LOFAR and SK at redshift 9 when pursuing a foreground avoidance in orange or a removal strategy in blue. And you can see that with foreground removal strategy, we can probe a larger scale and even increase our sensitivity at other scales. But of course, this is a very hard problem and can lead to biases or even signal loss if not done correctly. So for the LOFAR EoR experiment, we developed a method to do that based on Gaussian process relation. So the idea is that our observed data can be decomposed into several components, one being the astrophysical source, which are frequency coherent, the mode missing, which are bit less frequency coherent, the 21 centimeter signal, which are uncorrelated on scale of megahertz, and other components like noise. For most of them, we do not have a functional form, but we know that they have very different spectral characteristics. So in the GPR framework, what we do is that we can build a statistical model prior made of a Gaussian process, and the Gaussian process can be fully defined by its covariance. And in standard GPR, what the covariance functions that we use are analytically defined, and we typically use a matter class covariance function. So the idea is to set a covariance function for the foreground for the 21 centimeter signal. They have hyperparameters like covariance scale and the variance. You can add any other covariance if you have more components in your observed data. And then with GPR, we optimize the hyperparameter given the data. We can then fit get the fit of the foregrounds, subtract it, which will give us filter data, and from that we can get the residual part spectra. So we use this method on many 21 centimeter experiments. The main one being on LOFAR, and here I'm showing you an example of its use on 140 hours of NCP data, NCP LOFAR observation at a redshift 9. So here I'm showing you frequency slice of image cube before GPR. This is a GPR fit, and this is after GPR, and you can see that GPR removed the frequency current part of the signal. And the residual power here is quite close to the noise, even if you still have quite a lot of systematics left in this data set. And so this method allows us to set the deepest upper limit at redshift 9 with LOFAR. So we tried this method on other kind of data set, and here with Epoch, we tested it on a small test HERA data set. And so the interesting things that I want to show here is that in this small test data set, there was the presence of mutual coupling that were showing up at a specific K parallel that have been that the HERA team have been able to mitigate afterwards with a different method. But here we were able also to mitigate it with GPR by adding a periodic component to our covariance model. And with this, we were able to remove these mutual coupling systematics quite well as well. So the difficulty of the GPR method resides in defining the right prior covariance, because a strong mismatch between the prior covariance and the true covariance can lead to biases. So for now, we used only generic covariance function, but we need more physically motivated covariance prior in order to improve the method. But it is quite difficult to define analytically covariance function for the foregrounds or the 21 centimeter signal that could encompass all the full complexity of the foreground or the 21 centimeter signal. And only simulation can do that. So we can build a large set of foreground simulation, including the full sky, including the beam, polarization leakage, atmospheric effects, all that we can do. And for the 21 centimeter signal, we do have that as well. We can build a large set of simulation from different simulation code, like 21 centimeter fast, Grizzly, or the Llama simulation code as well. But how do you plug this kind of simulation to the covariance function for GPR method? And the solution is, of course, with machine learning. So we use here an autoencoder, for which the input of the encoder part are the covariance of the foreground simulation for the foreground part, and the output of the encoder is in the latent space. And then after training this autoencoder, we use the decoder as the foreground covariance. And so the foreground covariance, the input of the hyperparameter is the latent space, and the output is covariance that you can plug into GPR. And for the 21 centimeter simulation, you can do the same. We also have an autoencoder with input per spectra. And this also gives us 21 centimeter covariance, which is defined in the latent space as well. And then the GPR framework stays the same. only we now sample the hyperparameter with MCMC so that we can get a full uncertainty on the hyperparameters that we can propagate to the power spectra. And so to test this simulation, for now we have only the 21 centimeter simulation part of this new framework that we have been testing so far. So we set up a simple
5
simulation
minutes left.
where we train autoencoder using 21 centimeter fast simulation, and we take a reference signal that we need to recover, which is not part of the training set. We set a simulated noise 5 times the variance of the 21 centimeter signal, and we use a foreground simulated using standard covariance function. And so you see that with a simple case where we do not have any foreground, we can recover the signal quite well. So this is the blue and orange lines here compared to the black lines, and we cover it a lot better than with the standard GPR. And when you add foreground to it, we can still recover it quite well. You just add uncertainty on your recovery. And what we found as well is that VAE, in this case, and IAE, which are the two autoencoders that we've been tested, perform similarly. Another thing that we wanted to look into this simulation is to see what happens when you add into the observed data an additional component that is not 21 centimeter of foregrounds, so an excess component, let's say. And so if you add this component and you do not account it in the statistical model that we set in GPR, you see that you recover actually the excess component, and that means that this method do not lead to overfitting. But when you are able to characterize this excess component and are able to define add it to the statistical model, we are able to recover the signal quite well and a lot better than with a standard GPR method. So this will be my summary. ML GPR improved on the standard GPR by providing more physically motivated spectral and spatial covariance. We perform simulation with an ML-learned 21 centimeter covariance that show excellent recovery of the signal even in the presence of excess component when it can be accounted for. But this is only the beginning. Our next step is to build ML-learned foreground component for LOFAR and UNIFAR observation, including typical systematics, and also to build ML-learned 21 centimeter component from a larger set of simulation, like a Grizzly or the Lerma code, and including the cosmology as well. Thank you.
Thank you, Florent. Any question? Let's just give a few seconds for people to write on the Slack. I'm checking also if some hand is raised. David, can you?
Yes.
Your hand raised.
Thank you. So I just have one basic question. Could you maybe explain a bit more the difference between variational autoencoder and this interpolatory, or how is it called?
All right. So I will not be able to go into detail. So interpolatory autoencoder is something that Jérôme Bobin has been developing recently. So it uses anchor point. So you can define anchor point in the data that you want to train. So that you can, so the main advantage of this method here is that you can train on a data set with a small number of, with a small data set, let's say, but still be able to perform, yeah. basically, it's yeah, you can decrease the size of the training set.
Okay, thank you.
Thank you, Florent. So I think we have to move to the next speaker. Otherwise, you can make question again on this dedicated Slack channel. So next speaker is Saba Etezat Radzavi from Sharif University of Technology, and she will talk about constraining IGN temperature fluctuation between redshift 3 and 4 using SQ100.
Hello.
Saba, the floor is yours.
Hi, yeah. You should be able to see my screen now. Hi, I'm Saba, and I'm undergrad student at Sharif University. And I'm going to present the work that I've been doing with Sarah Buzman and Frederick Davis in Max Planck Institute for Astronomy on constraining IGM temperature fluctuations during the epoch of helium reionization using XQ100. And I will just give a quick background because most of the things here were about hydrogen reionization. By arriving around redshift 4 and 3, and which is the peak of quasar activities, we expect that the energetic UV background by quasar start to ionize the helium in IGM. And because this ionization process is extremely local and patchy, these quasars first start to heat up their own local environment. And it means that at some epochs, we expect that there exist some parts in IGM that are hotter than the other parts and consequently more opaque as well. And it means that there should exist some temperature fluctuations in IGM at the halfway point of helium reionization. And now the question is whether these temperature fluctuations are large enough to be observable by our observations or not. And the method that we're going to present now is it's based on observing transmissions in Lyman alpha forest. We have individual sightlines from quasars, and we do a binning problem on the sightlines, and we measure the mean optical depth and mean transmission in each of these bins. And we compare this mean optical depth and these individual sightlines with each other. And if we see like a difference between optical depth in these on two individual sightlines, then it's just the sign of existence of temperature fluctuation as well, because temperature fluctuations will result to optical depth fluctuations in Lyman alpha. And this is actually the advantage of our work in comparison with previous power spectrum works that we're looking at these individual sightlines, and it means that we're more sensitive to these fluctuations in IGM. And now the problem will be to actually measure these transmissions in observationally. And the data set that we're using right now is XQ100 legacy survey of 100 quasars between redshift 3.5 and 4.5. And we reconstruct the quasars continuum on Lyman alpha forest using PCA method, specifically PCA method by Davis et al. 2018 with corrections of Buzman et al. 2021. And having this reconstructed quasar continuum with quasar spectrum itself, we can measure the transmissions in Lyman alpha forest. And we apply a binning problem on Lyman alpha forest, and we chunk the Lyman alpha, and we measure the average optical depth in each of these bins. And then we also mask like every DLAs, and we're only looking at Lyman alpha forest away from proximity zone of the specific quasar. And after that, we apply a validated condition on each of these bins that we accept only the bins that at least half of them be usable after the masking. And this way we can have our optical depth distribution observationally. And having these observations, now we're ready to compare our observations to hydrodynamical simulations to actually use this to constrain temperature fluctuations. And the specific hydrodynamical simulation that we're using is NICS with this set of cosmological parameters that you can see here. And we don't have any ionization source in the simulations right now. And the only source of temperature fluctuations here is just density fluctuations, temperature fluctuations that arise from density fluctuations. And we pick randomly 40,000 sightlines in each redshift bins from these NICS hydrodynamical boxes. And to mark the effect of excess temperature fluctuation, because of our reionization source, we use a toy model of log normal temperature fluctuations, and we add a temperature fluctuation to a full chunk, like to a redshift beam, and we get this temperature fluctuation from a log normal distribution. And to actually add it to our simulated sightlines, we should connect these temperature fluctuations to fluctuations in optical depth. And to do so, we use Bolton et al. 2005, that they used a large set of hydrodynamical simulations, and they simulated these simulation boxes with lots of cosmological parameters to find the scaling relation for hydrogen ionization rate, which is a function of like optical depth, temperature, and other cosmological parameters. And by solving that equation from Bolton et al. For optical depth and temperature, we arrived to this equation that I have now. And this way, having a value of temperature fluctuation, we can relate it to extra scatter in optical depth, and we add this optical depth fluctuations on top of the existing optical depths that we have in our simulations. And we post-process all the simulational sightlines in 4 steps, as you can see in this plot. We downsample them, and then we add temperature fluctuations, and we add instrumental noise from X-shooter, and we also add continuum error from PCA. And this full forward model simulations NICS without temperature fluctuations. You can see in the CDF, the blue shaded area is NICS without any temperature fluctuation. And for all the redshift beams that we have, it seems that NICS is in a great agreement with our observations. And we're adding 50% temperature fluctuation, they start to disagree with our observation, which means that we can use our observation and this method to actually put an upper limit on the amount of temperature fluctuations. And to do this more precisely, we use a maximum likelihood measurement. And this way, that first our first step, we measure the probability of each specific observation I, given a temperature, given an amount of temperature fluctuation. This way that at each step, we post-process 5,000 simulated sightlines with error model corresponding to that specific observation I, and we draw a KDE out of the simulated optical depth, and then we measure the two-sided probability of this specific observation and this KDE, and it will be the probability of this specific observation. And the likelihood of our observation given temperature fluctuation model will be the product of these probabilities for all the quasars in one beam. And and in step 2, we need to measure the probability of drawing an observation-like sample out of simulations. And we just repeat the same process as before, this time for randomly drawn simulations. And we repeat it for n number of simulations, which n is the number of quasars on that specific beam. And this way we have a number of simulational likelihoods. And we can draw a KDE out of these simulational likelihoods. And to measure the probability of our observations given this specific amount of temperature fluctuation, we just need to evaluate this KDE, simulational KDE, on the this observational likelihood. And you can see in this plot that the blue histogram is this simulational KDE, and the red line is our observational likelihood. And in this specific beam of 3.9, adding more and more temperature fluctuations, our observations starts to get unlikely given the given model. And it goes to the tail. And here I arrive to my final plotting result that we measure the p-value of this observational likelihood on that KDE. And this plot is the p-value versus the amount of temperature fluctuations. And we repeat the procedure, this maximum likelihood procedure for 4 redshift beams, 3.7, 3.9, 4, and 4.2. And we did this for 2 separate scales as well, 100 megaparsec and 50 megaparsec, which is the size of the beam that we're adding the same temperature fluctuation to them. And our first result, which is expected here, and you can see, is that the dashed line are corresponding to the scale of 50 megaparsec, and the continuous line are corresponding to a scale of 100 megaparsec. And you can see that our analysis is more sensitive to temperature fluctuations on larger scales for all these redshift beams, comparing the continuous lines and dashed lines with the same color. And it's just because in smaller scales, there exist larger density fluctuations. And because of these density fluctuations, we cannot observe the signal of X-ray scatter because of reionization. And we also have a minor result that you can again see in this plot, that for redshift beams of 4 and 4.2, it seems that our analysis slightly prefer temperature fluctuations larger than 0 for the green line and pink line that you can see here. And this is not statistically significant because the model without temperature fluctuation is still in our 1 sigma, but together with our final result that I'm going to present in next slide, it may suggest that there exists an early reionization phase in IGM. And this is my conclusion plot, that it's the our constraint on temperature fluctuations for each redshift beam at 2 sigma and 3 sigma level. And you can see that given this plot, we can constrain temperature fluctuations as large as 25% at 2 sigma between redshift 3.7 to 4, and temperature fluctuations as large as 50% at 3 sigma. That given existing literature and models for helium reionization, many of them predict temperature fluctuations as large as 50% at the halfway point of helium reionization. So our model, our observations this way suggest that helium reionization halfway point should have been earlier than redshift 4 or later than redshift 3.7 to be in agreement with those models, or that the quasars responsible for helium reionization have had a short ionizing lifetime, that these fluctuations cannot be large enough for us to be observed, like they were smaller than our limits. And yeah, and I arrive at my summary and discussion. We measure optical depth distribution in IGM using these XQ100 quasars, and having this optical depth distribution, we compare our observations with mixed hydrodynamical simulations, and we try to constrain temperature fluctuations by this comparison. And the model that we're using now is just a totally normal model for temperature fluctuations that does not capture any effect of reionization on temperature density relation. But having a more realistic model, it just results to more extreme optical depth fluctuations. And it means that our bounds are already conservative. And again, our most important result, that we can rule out temperature fluctuations as large as 25% at 2 sigma and 50% at 3 sigma between redshift 3.7 to 4. And I guess that's it. Thank you for listening, and I'm happy to take questions.
Thank you, Saba. So I already see 2 hands raised. Andrei, I think you were the first.
Thank you. Very nice talk. I was just curious if you tried playing, or if you checked how much do your priors on delta T impact the results, because putting in a prior on something that's kind of empirical, like delta T, is not straightforward, especially if you want to tie it somehow in redshift as well. Have you checked how priors impact your conclusions?
The prior that we're using right now is just a flat prior on delta T, and I don't think that changing the prior actually changed the result, but changing the distribution of these temperature fluctuations will definitely change the result. That it's in the next step of our work that we're going to investigate.
Sorry, it's a flat prior but over what range then?
It's over 0 temperature fluctuations, 0% to 200%.
200. Okay. Okay, thank you.
Then there is another hand raised, Prakash.
Yeah, so Saba, very nice talk. I was curious to know about this. You detect the temperature fluctuations on large scale and not on the small scales. You mentioned that it is because of the density fluctuations, but do you think that it could be due to the observations? Because X shooter is at 34 kilometers per second. In order to resolve the absorption line, you need a resolution of 6 kilometers per second.
It can be, yeah, it can be because of observation, and we were actually discussing this before as well. But at the halfway point of reionization, we still expect that these temperature fluctuations, we see the effect of them on larger scale in the halfway point, because most of the temperature maps that we have during reionization, this scale goes to like 50 megaparsec to 100 megaparsec in the halfway point. So if we expect that halfway point be around 3.7 then 4, then it means that these models are ruled out already. But I cannot say anything else about other scopes. Like the final result is that this halfway point should have been earlier or later, but I cannot say anything else about other things.
Yeah, thanks. Yeah.
Because we still expect that at least half of the box be ionized in halfway point.
Yes.
So.
Thank you, Sarah. I don't see any other hand raised. Otherwise, as always, Slack channel is available. I think we can go with our last speaker for this session, Christian Hellum from the University of California. He will talk about a very accurate 21 centimeter global signal emulator with 21 centimeter VAE. The floor is yours, Christian.
Okay, can you hear me?
Yeah.
Okay, great. Yes, thank you. Yeah, so I'm Christian. I'm a grad student at UC Berkeley, and this is work I've done in collaboration with Stefan Portillo of University of Washington and Anastasia Fialko at the University of Cambridge. And we're introducing a new 21 centimeter global signal emulator called the 21CM VAE. So just some background. This is probably been covered a couple of times already, but the main point is that the astrophysics of the early universe should leave sort of direct traces on the 21 centimeter line. But these astrophysical parameters are largely unconstrained. They have, they're largely unconstrained. But there's currently a lot of observational effort in the 21 centimeter field. On the global signal side, there are experiments such as EDGES, HERAS, MIST, PRISM, and so on. And there's also one reported detection by the EDGES team. But with all this experimental effort, we expect data to come out in the next few years or in the current decade. And to derive parameters, astrophysical parameters from the data that these experiments will publish, we need tools that can generate theoretical models both quickly and very accurately. And full-scale sort of numerical simulations take order hours on standard desktop computers. So if you use parameter fitting tools like Bayesian inference, that's just not feasible because you have to generate these theoretical models a lot of times. So for that reason, there have been some emulators that have been published that use machine learning methods to relate the astrophysics to the 21 centimeter realization. And these include 21CM GEM, which this work largely builds on, and then global MU, which will be talked about later today. And the way we, as I said, 21CM VAE is this new code that sort of builds on 21CM GEM, but we aim to make the whole prediction algorithm much more simple. We want to rely more on the neural network's ability to capture all the complicated relation between the parameters and the global signal. And we don't impose any astrophysics. We don't have any we don't treat different types of global signals differently. We just use one neural network and let that do all the heavy lifting. And it's written in sort of this high-level TensorFlow code in Python, and it's all open source and on GitHub, which should hopefully be both easy to understand and easy to modify by the astrophysics community. And so the architecture is quite simple. There's one neural network using this 7-parameter input. So we parameterize the astrophysics with these 7 standard parameters. Some describing star formation, some X-ray heating, and then reionization. And it just fed through a series of hidden layers that use all the activation function ReLU, and it outputs this realization of the global signal over a redshift range 5 to 50, with a resolution of 0.5 in redshift, so that should be a 451 dimensional output. And the dataset we used is the same as 21 cm GEMS dataset, which is 30,000 global signals. We split it into training, validation, and test set. And on the right-hand side, you see a sample of these signals, what they look like. And we evaluate the performance of the emulator with the RMS error divided by the amplitude of the global signal. And this is the same metric that I believe both 21 cm GEM and global MU use, so they should be easily comparable between the 3 emulators. We train for 350 epochs. We use early stopping, so it stops a little bit earlier to prevent overfitting. And we also use the Atom optimizer in this training, and that sort of has some inherent randomness to it. So to avoid or to mitigate any random effects, we train 20 copies of the same emulator. The emulator we present here, the results we present will be from the best version of it, but in our paper, we show the distribution of all 20 of them. It turns out that the results don't vary significantly between the 20 different copies. So here are the results of 21 cm VAE. The left-hand side shows the distribution of errors on the test set. So the test set is about 1,700 signals. Again, yeah, the error is RMS divided by amplitude. And you can see that this is, in terms of accuracy alone, it's a significant improvement over 21 cm GEM, which I show the results here. So most errors, or the median error, is about 0.29%, which translates to 0.5 millikelvin. And you can see 95% of the signals are about 0.66%, below 0.66%. And even the 95th percentile is well within sort of the current noise level or systematics on current experiments. And we're also sensitive to changes in, if we vary the parameters by 1%, we computed that should make a difference of about 0.7 millikelvin on the global signal. So on average, we're sensitive to these 1% changes in parameters. The right-hand side shows these examples or examples of plots for 4 different global signals. So the 10th percentile, median, 95th, and the largest error. And so just by the eye test, you can see that the median error, it's almost impossible to distinguish the predicted signal, which is in orange, and the simulation signal in blue. On the 95th percentile and the largest error, there are more visual, like you can more easily see that it's the emulator struggles at this turning point here. But in general, you can see from this distribution that the errors are shifted towards very, very low percentages. And with 21 cm VAE, we sort of explored what's going on. So the last hidden layer is 224 dimensions, and that's just a representation of the global signal. And we used the t-SNE technique to project these 224 dimensions onto this 2-dimensional plot. So here you see 9 copies of the same 2-dimensional plot, and each is colored with the value of the parameter. So for example, this shows that in panel A, you can see how F star is organized in the last hidden layer of the emulator. And the more a parameter is separated in these sort of plots, means that the more the emulator had to organize and structure the latent space to separate them. So it prioritized, to minimize the loss, 21 CMVAE prioritized separating F star, VC, FX, Newman, and so on. And using this, by looking at this, we can see that because it prioritized these parameters, so F star and VC correspond to early star formation, FX and Newman correspond to early and strong heating, and also in H and I, you can see the combinations of these parameters. That indicates that both the two most important or dominant astrophysical processes over this redshift range 5 to 50 for the 21 centimeter line are early star formation and the amount of X-ray heating, whereas the reionization parameters, tau and the mean free path, are less important. Like, they're not separated in this representation of the latent space. We also, in the paper, used a more quantitative metric looking at derivatives of the global signal that I don't have time to go in depth on, but long story short is that it sort of agrees with this picture of, or this sort of qualitative interpretation of what processes that are most important. So just to summarize, the 21 centimeter line can trace this astrophysics of the high redshift universe over an unprecedented large redshift range. And there's a lot of observations coming up. And 21 CMVAE is a new tool that can be used that's both fast and accurate, that hopefully experiments can use to derive parameters from observation. And by analyzing it, looking at both the visual representation and the quantitative derivatives, we can also extract what processes are most important in different frequency bands. Yeah, so thank you, and I'll be happy to take questions.
Thank you, Christian. Looking quickly in the chat or the Slack if there are any written questions. Otherwise, I guess I have a question for you. Have you tried, you mentioned at the beginning that your variational autoencoder can be tuned with different alternative, let's say, heating models? Have you tried anything on this side? Or?
No, so we've simply trained it with the current data set, but it should be very straightforward to retrain the emulator with any new data set that you might have. Yeah, so that's probably future work.
Okay. And do you provide, can you even provide some sort of prior in your variational autoencoder, or is completely randomly, how to say?
Prior on the, what do you mean?
On the, yes, yeah.
Sorry?
Yes, in the input parameter that you use for your
well, if you want to use 21 CMVAE, so I'm not sure I understand, but for the training, the way that these parameters are, they're sampled, like we inherited this data set from 21 CM Gem, and yeah, I'm not sure if you use this, if you use 21 CMVAE in a Bayesian sampling, then you can sure set your own priors. Yeah.
Okay. Maybe I think a bit more on this question and I write you better.
Okay, yeah.
Formulate it better.
Sure, just on Slack or something.
Sure. Don't see any other question. Otherwise, I think we can have a short break. We can otherwise have a short break and come back at quarter past, so in 10 minutes, sorry, in 15 minutes. And after that, we will have 2 more talks and a final discussion on these 3 days meeting. Okay. See you in 15 minutes. Cheers. Hi, can I quickly ask to the next two speakers, Sudipta Sikder and Harry Benbis, to check if their screen sharing and full screen presentation works?
Hi. Yeah.
Hi, Sudipta.
Just a second. Yeah, can you see the screen?
Yeah, it works. Full screen, perfect. Thank you. And Harry Bevins.
Hey, sure thing.
Yep.
Can you see that?
Yeah, full screen.
Nice.
Okay. Thank you. Okay, so see you in about 4 minutes. Sudipta, you're the first.
Yeah.
Okay, it is 1/4 past. I think we can restart. I see people are getting back into the Zoom link. Just wait a few seconds and then Sudipta, I think.
Yeah, can I share my screen?
Yeah, can. Okay, I don't see more participants getting in, so I think we can start. So, okay, next talk is Sudipta Sikder from Tel Aviv University, and he will talk about some machine learning to decipher the astrophysical process of cosmic dawn. So, Sudipta,
Okay,
the floor
thanks
is yours.
for this introduction. So in this talk, I'll present the machine learning approach to decipher the astrophysical processes at the cosmic dawn. So let me first start with what kind of astrophysics can be extracted from the 21 centimeter signal. So we use 7 key parameters to parameterize the high-redshift astrophysics. The star formation efficiency quantifies the amount of gas in the dark matter halo, which can be converted into the stars, and the minimum halo circular velocity is another parameter which encodes information about the star formation. And then there are X-ray efficiency and X-ray ACD parameters, which encode information about the X-ray radiation of the early universe. The CMB optical depths and the mean free paths of the ionizing photon are the two parameters that describe the epoch of reionization. And currently, we almost have almost no observational information about the values of most of these parameters we used in this work, except for the optical depth of the CMB. And for the second part of this work, we used two more parameters to quantify the excess radio background. And I'll get to that later in this talk. So we used our own semi-numerical simulation to generate the 21 centimeter power spectrum for various astrophysical models. Around 3,000 models have been used as a training dataset, and we use a test dataset of 100 models. And for this work, we use the artificial neural network. And while using the machine learning algorithms, data pre-processing becomes an important step. And for our work, we used two pre-processing steps. One is the standardization of the datasets, and another is the dimensionality reduction. For standardization, what you do, we just transform all the features to the comparable scales. And for the dimensionality reduction purpose, we used PCA, the principal component analysis, to project the dataset into the lower dimensional space. And using PCA actually speeds up the learning algorithms. So we not only generate the 21 centimeter power spectrum without any observational limit, we also consider a realistic case study where we create the mock SK dataset, including several observational effects in the 21 centimeter power spectrum. For that, we include the effect of SK resolution, and we add a pure Gaussian noise that are smoothed over the SK resolution as a realization of the SK thermal noise. And we also add the residuals from the foreground avoidance, where we just assume that the part in the K space that are dominated by the foreground is removed. And for this mock 21 centimeter mock SK power spectrum, we also use these 5 K bins that are evenly spaced in log scale, and 8 redshift bins between Z equals 6 to Z equals 27.4, which corresponds to the frequency 50 megahertz, the limit for the scale. Okay, so the procedure goes like this. So we have a trained artificial neural network, which given the 21 centimeter power spectrum over a wide range of redshift can predict the 7-parameter model. And we also train an emulator which can mimic the 21 centimeter power spectrum given the 7-parameter models. And we employ this trained emulator to a MCMC sampler, and we use the predicted parameter from this step as the initial guess in the MCMC sampler. So the final output is the parameter and their respective uncertainties. So here we just show some of these example of the comparison between the emulated 21 centimeter power spectrum and the true power spectrum from the simulation. Here we can see that the accuracy of the emulator is generally well, but there are some random variations over different models. And here we see both the cases, the case without the SK noise and the case with SK noise for a particular wave number. Okay, so as I have already mentioned, the final output is the posterior probability distribution. Here is an example where these red lines and the red crosshairs are the true parameter values, and the green lines and the green crosshairs are the best fit parameter values. Here we can see that for several parameters, the true parameter values lies outside the 1 sigma uncertainty estimated by the MCMC. So, which implies that the MCMC uncertainties significantly underestimate the true error bound for several parameters. So, to handle this problem, to get the more reliable errors, so we use ensemble of emulators that are trained using several subsets of the training datasets. After including the ensemble learning technique in the framework to evaluate the overall performance in predicting the parameters, we just used this normalized error where we compare the true parameter with respect to the predicted parameter. Here sigma prime is the uncertainty after including this ensemble learning method in this framework. And if this sigma prime is an accurate error estimate, and then the actual values of these errors should have a standard deviation unity. So here we see some of the histogram of errors for 4 parameters. Here we see that this solid black line is a Gaussian fit for the respective histograms, and the standard deviation and the mean of these Gaussian fits are mentioned in the respective panels. And we see for almost all these parameters, this standard deviation is close to 1 or within 20%, which means that we are able to generate a good estimate of the uncertainty using our procedure, and the mean, which actually measures the bias in the prediction, which is smaller than like around 0.3 sigma in size. So if we use the mock SK power spectrum, we see that in that case as well, the standard deviation is close to 1 or within 20%. But here the mean for some of these parameters are as large as 1 sigma, which means that adding SK noise to the power spectrum increases the biasness in the predictions. Okay, so here we see some of the histogram of sigma prime for three parameters for both the cases, without SK noise and with SK noise. So here we see that with our procedure, the F star can be reconstructed with an accuracy of 8%. And for VC, the accuracy is around like 3%. And Fx is uncertain by a factor of around 3.1. And while using the mock SK power spectrum, we see that this error increases up to 32% in F star and 15% in VC. And some of these parameters, including Fx, they are marginally affected by these SK effects. Okay, so in order to understand the emulation error more deeply, we try to estimate the error and how it varies along the redshift and the wave number. And for that purpose, we use this definition, and the median is taken over the test data, test models, which is like 100 models. And here, this definition actually estimates the relative error, but there in this denominator, we have one constant in order not to demand the low relative error when the fluctuation itself is low. So here in the left panel, what we see that we use the true parameters from the test data set to emulate the power spectrum, and then we just calculate this error. And we see that the error decreases with the increasing wave number up to k around 0.1 or 0.2. And then there is this plateau region, and then the error again increases after k around 0.6.
5 minutes left.
In this case, we see that the in each k bins and redshift bins, the error is around like 10 to 20%. And when we just use the base fit parameters derived from the derived from the network without SK noise, we see that these are more or less like similar if we compare the left panel and the middle panel. So if we compare it, we can say that the fitting is nearly perfect. That means the error it adds is generally smaller compared to the error of the emulator itself. And in the right panel, we see when we use the base fit parameters derived from the network with the SK noise. And here we calculate the error in the ability to reconstruct the power spectrum without SK noise. So if we compare the middle panel and the right panel, we see that the SK noise increases the typical error up to an order like around 1.5. This is because of the SK noise. It is this SK noise actually makes it harder to reconstruct the parameters more accurately. Okay. So let's move on to some non-standard astrophysical model. So one of the possible explanation for the edges signal from Z around 17 could be the excess radio background. A uniform external radio background can contribute to this excess radio excess, and in that case, the amplitude of the radio background is the parameter we used, which is called AR. And another potential model is that radio background is originated from the high redshift radio galaxies, and for that the parameter is FR, which is the normalization of the radio emissivity. So in the second part of this work, we used both this kind of radio background to train an artificial neural network, and we asked the question whether this trained network can identify the type of the excess radio background present in the signal. So here we see the confusion matrices for the two cases, both without SK noise and with SK noise. And for the case without SK noise, the accuracy of classification is around 99%. And when we add SK noise to the power spectrum, we see that the accuracy drops down to around 87%. So let me summarize here. So we find that the numerical emulation method is computationally efficient, and given the nonlinear dependence of the 21 centimeter power spectrum on the astrophysical parameters, this emulation method based on the artificial neural network could be very useful to extract the astrophysical information from the upcoming 21 centimeter observations like SKA. And we found that fitting the mock SK data results in a typical accuracy of 5% in the CMB optical depth, 30% in the star formation efficiency, and a factor of 3.5 in the X-ray efficiency. And just to mention that most of these parameters, except this CMB optical depth, they are unconstrained. And we also found that a trained neural network can identify the nature of the excess radio background if it is present in the 21 centimeter signal. And if you are interested in the more details of this work, you can find it in the archive. That's pretty much it. Thank you.
Thank you, Sudipta. Do we have questions? Quickly check in the, someone raise a hand for this question in the Slack channel. Otherwise, I do have a question on how do you binning, so have you checked what's happened when you bin what does happen when you have a different binning for your redshift? Because I expect that, for example, for larger or smaller binning, redshift binning, USK noise will vary. So how does this affect your error?
For our binning over redshifts, so the idea is like we have this redshift which starts from like 6, and the maximum redshift for SK is 27.4. So so if you see the distance, the co-moving distance between these two redshifts is around like 3000 megaparsec, and our simulation box is the size of this box is around 384 megaparsec. So in between these redshifts, we just we can put like 8 redshift bins, and we just add, we just average this 21 centimeter power spectrum over this particular redshift bins that are spanned by each of these boxes from the simulation. Is that the answer yours?
Yeah. Yeah. Okay. Nice. Yeah. I also see there is an additional question by Yimao. Yimao, if you want, you can speak up. Or...
Hi. Yeah. So so you put a lot of efforts in testing the emulation errors. So I'm just confused here. Is it just test, or did you include that emulation error into the inference results when you do the MCMC?
So can you repeat the question, please?
I mean, the test of the emulation error are just test, or when you do the MCMC inference, you incorporate the emulation error into the inference?
No, so when I show these results, this is just the MCMC. This is the case without any without including the error. And after we use this ensemble of emulators, and then we just add this error to this MCMC, and that is defined by the sigma prime.
Sorry, Mikhail, I think you're muted.
Yeah, sorry, I forgot to mute myself. I was saying, we have, thank you, Sudipta, for the talk. We have the last speaker for this session, just before the final discussion, is Harris Thomas John Bevins from the University of Cambridge, and he will talk about global EMU, a new and robust approach for emulating SKA average centimeter signal from cosmic dawn to Epoch of Reionization. The floor is yours. Harry, you're muted.
There we go. Can you hear me?
Yes.
Okay, nice. Yeah, so thank you. My name's Harry. I'm a third year PhD student at Cambridge, and I'm going to talk to you about global EMU. So this is a novel and robust emulator of the global 21 centimeter signal using neural networks. So kind of just to motivate the problem, why we need these neural network signal emulators. So the global signal can be modeled in lots of different ways. For example, using Gaussian profiles, or in some cases, flattened Gaussian profiles. But ideally, we want a model that informs us about the physics of the cosmic dawn and the epoch of reionization. And we could use direct semi-numerical simulations to model the signal, but these take sort of on order hours per signal to generate. So neural networks have been shown to be a useful proxy for these simulations that can generate signals in sort of order milliseconds, which is much more practical if you want to use these signal generators in, say, nested sampling runs. So I'm going to focus on the differences here between global EMU and 21 centimeter GEM. And as I say here, this has previously been explored with 21 centimeter GEM, and as you heard earlier, more recently with 21 centimeter VAE as well. But looking specifically at 21 centimeter GEM, this kind of emulator relied on about 5 or 6 different neural networks and a decision tree, which classified how many turning points were in the global signal. And an example of one of these networks took in 7 astrophysical parameters, some additional derived parameters, and it gives you out PCA components that you can then reconstruct into a global 21 centimeter signal. What we've done differently with global EMU is that we've reparameterized the problem so that we now have redshift as an input to our neural network alongside our 7 astrophysical parameters. And that means we get a single corresponding temperature out the other side. And we have to run like a for loop or a vectorized call to this emulator to generate an entire spectrum, but we don't find that this hinders the performance at all. So we really want to make a comparison to 21 centimeter GEM, and we use the same training and testing data that was used to evaluate that neural network. This corresponds to about 30,000 training models and about 2,000 test models. Global EMU is also capable of emulating the neutral fraction of hydrogen. So we have about 10,000 training models and 800 test models to demonstrate this. And both these data sets rely on the 7 astrophysical parameters that you've seen in the 2 previous talks. So these are things like star formation efficiency, the X-ray efficiency, and the total CMB optical depth. But we want to point out that Global EMU is a very flexible Python package that can be easily retrained on any set of semi-numerical simulations, and it doesn't necessarily have to rely on these astrophysical parameters. But once we've got our training data, we need to think about our pre-processing of that data, and we try to use a very physically motivated pre-processing to make the problem as simple as possible for our neural network to solve, so that we could keep a very small structure and rely only on a single neural network. So for our global signals, all of the signals in the training data have a common behavior at high redshift, where they rely on cosmology rather than on astrophysics. So we can model that behavior and remove it from our signals before we give them to the neural network. Which means that the neural network is not spending time trying to learn something that's very trivial at high redshifts that we can add back in later after emulation. We also resample the signals so that the sampling is highest around regions of high variation in the training data. And then we divide the global signals by the standard deviation of the entire training data set, which means that they're of order unity when they go into the neural network for training. So you can see in this graph what the global 21 centimeter signals look like after we've done our pre-processing. And you can see that they've been stretched out so that the parts of the spectrum that are highly dependent on the astrophysics have really been emphasized for the neural network to learn. For the neutral fraction, they're already of order unity, they're between 0 and 1, and there isn't really an equivalent astrophysics-free baseline at high redshifts that we would benefit from subtracting from these models. So we just perform the resampling, and again, you can see in this graph that stretches the signals out and really highlights the regions where the astrophysics dominates the structures of the signals. For our astrophysical parameters, we perform a min-max normalization. In some cases, this is on the logarithm because it's log distributed in the training data. And then for our input redshift, we also perform a min-max normalization, and we input this as a uniform distribution, which again means that the neural network is seeing these signals as if they've been stretched out. And there's much more detail about this in the paper, which you can go and have a read of after the talk as well. But having kind of reparameterized the problem, so we have redshift as an input, and doing this physically motivated pre-processing, the idea here was that we would keep the neural network as simple as possible so that people could understand what was going on. Perhaps people that didn't have like a background in machine learning could pick this up and understand what's going on. But we do have to think about some neural network specifics. So things like our loss function, we use the mean squared error loss function. And our optimizer, we use an Adam optimizer. And these are two very sort of standard choices for neural network problems. And then we set a target accuracy that's on average, an average RMSE of 2.5 millikelvin, which is approximately 10% the expected noise of the REACH Global 21 centimeter experiment. And the idea here was that we were going for something practical rather than constantly trying to improve our accuracy and getting diminishing returns for the effort that we're putting in to do that. So we can test a series of hidden layer structures for our single neural network, and we pick the first kind of hidden layer structure that meets this target accuracy for our testing data set. So having thought about our neural network specifics, we can then go ahead and train on our training data and test with our 2000 test models. And in the redshift band, z equals 7 to 28, our mean RMSE is 2.5 millikelvin. So we're meeting that target accuracy. Across the broader band that we're emulating, so z equals 5 to 50, our mean RMSE is slightly lower, it's 1.85 millikelvin. And then in both of these redshift bands, our 95th percentile RMSE is significantly lower than the expected noise in a global 21 centimeter experiment. And there's only a few models in the testing data that have RMSE values worse than these 95th percentiles. For our neutral fraction, our mean RMSE is about 0.3%. So the emulation of the neutral fraction is actually a bit more accurate than the global signals. And this is kind of to be expected because the relationship between the astrophysical parameters and the neutral fraction is far simpler than between the parameters and the global signal. But we're meeting a high level of accuracy with both emulators here. And to compare this with 21 centimeter GEM, so I've just put out this diagram showing the difference in the two emulators again. We can normalize our RMSE metric by the maximum absolute temperature of the spectra. For global EMU, our max normalized RMSE is 6.32% when emulating that full testing data. And in comparison, 21 centimeter GEM gives a value of 10.55%. So that's a factor of almost 2 improvement in accuracy. But then more significant is our improvement in emulation time. For global EMU, our emulation time per signal, and these are high resolution signals with about 450 data points, is 1.3 milliseconds. And in comparison for 21 centimeter GEM, this is 133 milliseconds. So with global EMU, we're getting a factor of about 102 improvement in emulation time, which is particularly important if we want to put a neural network signal emulator inside a nested sampling loop, where we're doing sort of thousands of calls to generate signals. So then I want to reiterate that this code is very accessible and adaptable. It's pip installable, available on GitHub. It's fully documented, and this code snippet here is about 30 lines. It's a full pre-processing, training, and evaluation with some test data of a global EMU neural network. So you should be able to retrain this on any set of semi-numerical simulations you like. And once you've trained a version of global EMU, you can generate one of these nice graphical user interfaces where you can slide the sliders and see in real time how that affects the structure of the global 21 centimeter signal.
5 minutes left.
Okay, no problem. And then finally, I just want to point out that we have already used global EMU to perform some physical signal modeling in a reanalysis of the SARS-2 data. So here we retrain global EMU on some exotic astrophysical models with an excess radio background above the CMB. And then we fit this signal model to the SARS-2 data along with some foreground modeling, some systematic modeling, using global EMU for the signal modeling. And we get out parameter constraints and constraints on the global 21 centimeter signal. So you can go and read about this on arXiv, and this SARS-2 paper has been submitted to NGRST as well. So just to conclude, we've done this like reparameterization of the neural network so that we now have redshift as an input alongside our astrophysical parameters. And this in combination with a physically motivated pre-processing of the data has allowed us to keep the neural network very simple. We have a very simple structure. And that's led to a factor of almost 2 improvement in accuracy on the previous state-of-the-art emulator. And approximately a factor of 102 improvement in emulation time. The code's pip installable, available on GitHub, and we released some trained models on GitHub as well. But it's easily retrainable, and it's packaged with this nice graphical user interface to explore the parameter space. So you can go and have a read of the paper that's also been accepted by NGRST, and go and have a look at the code on GitHub. So thank you very much for listening. Are there any questions?
Thank you, Harry. I'm not muted now. Okay. Sambit, I see you have hand raised. You want to make a question?
Very nice work. I just have a question regarding the posterior distribution that you showed in the previous slide. I mean, here I see that all the 1D marginalized curves look flat. So does this mean SARS-2 data constraints nothing?
So the 1D posteriors here are flat, but you can see that we're ruling out regions of the 2D parameter spaces. So particularly if you look at the values of F radio and Fx. And often these 1D and these 2D posteriors hide correlations or like constraints in higher dimensions. So we can look at the functional prior shown here in blue and how that contracts to the functional posterior shown in red when we do our fitting. And you can see that the SARAS-2 data is ruling out a lot of these very deep exotic astrophysical models.
Right.
Next, I see Yima, you have hand raised.
Yeah, I guess I have the similar question to the previous speaker. So when you do the inference, did you include the emulation error in the MCMC, or just take it as ground truth when you do the inference?
When we do the SARAS-2 data analysis. Is that
Yeah,
what
when you
you're
do this inference from the real SARAS data.
Yeah, so we don't necessarily include the emulation error in our analysis. So this is a nested sampling run rather than MCMC sampling. But we note that the accuracy of our emulator is on average less than the noise in the SARAS-2 data. So we wouldn't necessarily expect that emulator error to play a significant role, I don't think.
Okay, good to know. I guess I just have a general comment because from the ground, I mean, from the exact sense, when people do this inference, in principle, you should include the emulation error because that's kind of systematic error, right?
Yeah.
I see that people do the emulation and all the way that didn't do that. So I guess that maybe somebody knows what's the exact way to include that in the analysis.
Yeah,
but we could discuss in the later.
Of course, you should definitely consider the emulation error, but you also need to think about the semi-numerical models as well. They have a error built into them from like our uncertainty in the physics. So like you have to include that
Sure,
as well.
understand.
Yeah.
Yeah, probably the question is more generic. How could we include the systematic error in the semi-numerical simulation or emulations, errors, etc., into the inference? I mean, because that's not just a flat bias. It's just it's like K dependent or the redshift dependent or whatever. So it's complicated.
Yeah.
We'll see.
Okay, thank you very much, Harry. If there is no more question, I think we can move on to the discussion session. It will be hosted by Isabella Carucci and Stephen Murray. If you, either Isabella or, yeah.
Hello, can you hear me?
Yes.
So yeah. Yes, with Stephen, we prepare some slides in order to summarize a bit what we have been hearing these days and try to trigger some discussion. So can you see my screen correctly?
Yes. Yeah, everything's fine.
Yeah, so I guess I'll start things off. So I made this word cloud of the words in the abstracts, and so I wanted to try to see, what is the story at the moment? What's the summary story of what we're talking about at this conference? And so, trying to interpret the many words in this from the most used to not. I think the story goes something like, what can we learn about the parameters of galaxies and reionization using observables such as 21 centimeter Lyman alpha and quasars by combining simulations and data/observations with novel models. And interestingly, whatever it is, we can and will do it. Apparently, they are big words in our abstract. So, that's quite positive. And I think kind of summarizes the overall tenor of this conference, which has been really super interesting. And so thank you to everyone who's done work on this and has presented their work. And I think the community here is definitely moving forward in terms of how we interpret the masses of data that are starting to come through and the simulations. so maybe go to the next slide. So what has this conference really taught us? So I think the big thing I learned was that grad students are babies, and we need lots of them. But no, I thought that was very funny. But in all seriousness, we should probably move on to the actual things we've learned. So I'll pass it over to Isabella.
Yeah, so here we try to summarize a little bit the whole 3-day meetings that we had. It was really broad. So we are talking about the high-redshift universe. So it means that actually we are dealing with astrophysics related to galaxy quasars and also to the 21 centimeter signal, both the fluctuations and the global signal. So it's a very broad in terms of topics in astrophysics and observationally. So different experiments and different techniques that we are dealing with. And then the key word of the 3 days has been learning. So here we try to summarize what we mean by this. So we can either learn directly from data. For instance, if we have some classification tasks like Lena presented, like looking for quasars in images, or Rodrigo with icy radio galaxies, or we can learn from data in order to fill the gaps themselves that we have in the data, like Romain with the damping wing in the quasars. Or we can learn from simulations. Well, first of all, we can speed up the simulations, like Mosima proposed an emulator, but actually we heard a lot of emulators. And we even heard about a way to speed up the emulator themselves, retaining the accuracy that you want. And then, of course, you want to learn something from simulations in order to apply what you learn on data. Like, for instance, for foreground cleaning, as Florian, as an example, told about just briefly earlier today. Of course, to do parameter inference or other things like calibration or map deconvolution. So here is a broad thing of all the things that we want to do and we are doing with these methods. So here we are talking about, again, it's really broad what we mean with the learning. So there are methods that are, we can see more traditional, more standard by now, like semi-analytical models, Bayesian model selections, MCMCs, and so on. There are things that are maybe newer, but more and more people are getting their hands dirty with these. So all sorts of neural networks, different flavors of autoencoders and so on, random forest decision trees, and maybe something more newish. We even heard one talk on the scattering transform that is getting some attention nowadays in astrophysics. So this is what we heard, and these are the questions that we were asking ourselves, and we prepare together to ask you as well, and to trigger some discussion. So we will briefly go through them, but then please just pick what you want so we can start. So first of all, I think the elephant in the room are the simulations and the training we do on them, because so what has been trained on simulation can be trusted in order to be used on data. For instance, Paco, this comparison among something trained on industries and then tried on Simba that wasn't so optimistic. And I think this question is linked to the second question that we have here. We also noticed that most of the talks that we heard, most of the abstracts submitted were leaned towards theory. So we are doing many things with these learning techniques on theory, not so much on data analysis. So I think these two questions are related. So like, how much do we trust these methods in order to actually apply them to observations? So what needs to be improved in order to have more competitive methods? And then again, there are tasks where maybe we already know, well, we already have evidences that machine learning techniques can improve over traditional methods. So probably classifications, like in order to discriminate among populations of objects, but also build emulators. But I don't know if you agree with these or if you want to add something. What needs to be done in terms of interpretability. And at the end, we could also discuss about, in terms of community, how can we optimize the work that we are doing? So of course, sharing the simulations, data, and the codes is very important. Is there something else that we are missing in order to work better and faster on this? So I hope these questions resonated and trigger. You want to say something about them? I don't know who wants to start.
I thought maybe we should start with the most maybe provocative question, which is the first one. I think, you know, how much do we trust our simulations on these things? And you know, I don't know.
Carolina, you want to say something?
Yeah, thanks for the great summary. And of course, thanks to all the speakers who really helped to kind of make a mosaic out of that and fill these questions with content. So yeah, for the simulations, yes, I think this really kind of, it folds, I mean, it's all kind of connected, as you said, like the simulators are connected to the kind of imbalance we have right now, that we look more at like simulated. I mean, we're still kind of like grad students, I think the babies that Stephen has shown in the beginning, like all of us, because we're trying these new methods and we're trying to raise them to a level where we can really like say, okay, we really trust them. And yeah, for that, we really need to test it on data. And also look at, yeah, uncertainties, calibration, all of these issues. So for simulation, I think it really depends on the question maybe you ask. You ask them. I mean, we have to test per different simulations against each other. It's very different, maybe not very, but different modeling. But also, yeah, really data. So I think, so what we tried, and I'm also curious to hear what people are trying to look at that, is that we had like very different levels of foregrounds, and then we we train on one and then we evaluate on the other one. I mean, this is now like deep neural networks. So just to see if they're still able, so what are they still able to get? But I think the best way probably to go is to really have good error bars in the end. If it's an inference task, of course, so it really depends on the question. Yes, I don't know what other people think about errors in simulations and all that. I'm happy to hear more.
Gareth, I see you raise your hand. You want to comment on that?
I just, when the question was phrased, I had to think of, I think it was Roger Blandford or something, who once said, I only trust other people's simulations. So if we all have that attitude, I guess it would be kind of interesting. So yeah, I was thinking actually with many of these simulators now, of course, it becomes more and more easy to go the other way. So for example, for the global signal, you can generate a global signal with a completely different code and then put it into, you know, an analysis based trained on this other code, and then, you know, that should give you an idea of how well this is going to work. And this is something we're and so it's also another important thing there is to go blind, because I guess we know in general that people are biased as well, right? So if you know what the right answer is, you're not going to do the outcome may be slightly biased. And so all of this is where there's a plan to do a comparison like that for in the context of SK, which so this will be based on the power spectra. So which Andre and Brad Greich and Sambit and I are preparing. So those of you who can interpret power spectra may want to be prepared for this. Okay, thanks.
Does anyone else have anything to say about this? I was thinking actually of the comments that were made at the end of the previous talk by Yimal, who was saying that, you know, these, well, and Harry mentioned this as well. So, you know, there's not only errors in the emulators, but there's errors in the the semi-analytic models, or the however you get your model in the first place to construct your emulator on. There are errors there because we don't understand the physics completely, and those kinds of errors aren't something that you can kind of just say, okay, we'll add, you know, plus or minus 20%. They're K dependent, they're redshift dependent. Propagating those through to the final uncertainties is, I think, very tricky. I'm not even sure how one would go about it. Andre.
Yeah, I just want to echo all that was said. I think it's important to characterize these errors, and errors in and of themselves are not scary. It's only errors that you cannot characterize statistically that are scary. So I think we should try to aim to as a community get together and characterize this, characterize the differences between, for example, different codes. I don't know what's the best framework for this, like a large praise proposal or something like this, but it's one of the kind of good discussion topics that we might want to do in something like the SK science team or something like this within some kind of a more global framework.
Yeah, and maybe also, as Garrett said, the data challenges are something useful for the community in order to test these things in a blind way, and with other people and with other people's simulations that are always better than yours. So that's also a good exercise.
I think testing is great. It's a good like sanity check. But what I was more getting at is like a systematic study where you kind of try all over parameter space to predict the same thing given the same input, and then find some basis where you can characterize these errors. As long as you can again characterize them, that's okay.
Mark?
Yeah, I just want to echo on the Andre's comments. So back to the question, I mean, the systematic error that we talk about on the errors from the semi-numerical simulations and from the emulation errors. I think this kind of errors are probably to different levels. So I kind of have an idea how can we incorporate the emulation error into the inference in the MCMC, but because that's kind of easier. But for the error in the semi-numerical, that's kind of we have a long history of discussing that because semi-numerical simulation and numerical are basically two different animals. I have to put this way because they have different parameterizations and so on. Well, although we can have some tricks to say put the two simulations in the same global history and then we compare power spectrum in this way to bypass the different parameterization, but how do we quantify the systematic error in the semi-numerical simulations are still a tough question. I think we don't have a consensus. Correct me if I'm wrong. So I think that's something, some error that I could put into the category of unquantifiable errors that is horrible in Andrew's words. So I leave it to you to decide. I mean, that's an open question, but I will stop here.
Yeah, I agree. And Harold.
Yeah, maybe to move it in a slightly different direction. The one thing that worries me about all these machine learning approaches that I guess was more or less the focus of many of the talks, is that, of course, the whole point is that we're going to use them in cases where we don't know the answer. Let's say, of course, we test them, etc. But how can we have, I mean, they're really black box, right? Simulations can be black boxes, but actually they're black boxes that we can open up and understand what's going on under the hood at some level. At least someone understands that because it was coded up in but with the machine learning algorithms, we have no clue. So this, it's almost, I mean, this is, I'm sure this has been discussed, it's almost a philosophical question, but I mean, how can we ultimately be confident that we're, you know, if we're using them in regimes where, I mean, for example, once a tool maybe comes out, how has it been documented, on what, you know, at what level it has been trained, under what, you know, circumstances have been trained? There should be like a big documentation with every machine learning tool, like, okay, only use it for this because it wasn't trained for all these other things. And I'm slightly worried that this may be forgotten at some point, or in some cases anyway. So, yeah.
That's a really interesting point. I think, I mean, just across the board, documentation for all of these codes is, and methods and algorithms and everything is extremely important. You know, characterizing the limitations of the method is always, you know, one of the most important things. And there may be somewhat more or less standard ways to be able to do this if we think hard enough about frameworks for that. Emil?
Yeah, I just want to comment a little bit on what was just said. I would say that there is the machine learning methods that are some level that they are black boxes, in the sense that normally they have too many parameters and we are not able to develop an intuition about what they are doing, in the same sense that we are able to develop intuition about other methods where we are able to handle all the parameters that are involved. But if we take a look, but they are, it is possible to mathematically describe what they are doing. What it's not possible to do is to give interpretation for each one of the parameters inside the model. But as a global thing, we can understand what the parameters, what the model are doing. And all of these machine learning, all of these algorithms, they are based on hypotheses about what is in your training data. So especially this, I'm talking about the supervised ones. So I really like the idea of having a very thorough documentation saying, this is what it was trained for, and this is what exactly I promised that you will do, because that thing we know, right? Maybe we don't have an intuition about how the algorithm is working in each one of its parameters, but there are very well established algorithms and very well established theorems that said, given the conditions and characteristics of your input data, this will work or this will not work for that specific task. So just food for thought.
Also, to follow, sorry, I tried to raise the hand, but as a co-host, I cannot raise the hand. To follow up to what just Emily said, there seems to be some effort also to understand exactly what is going on inside the neural network. Like, for example, I cannot remember the name of the speaker, but for the reconstruction of the quasar profile, where it was like freezing, let's say, some part of the low dimensional latent space and see what exactly change in the output. And if I remember correctly, there was some, I don't know, the H1, the Lyman alpha peak was more pronounced or so.
Yeah,
Also, I think
it could connect the latent space to actually to the physics at the end.
Yes, yeah. To see at least, I mean, not to see, but to have a kind of an idea what the network is representing with this parameter. Also, I think Yuan Senting in the Australian Pacific Asian session say something about this transversal learning. I quickly rewatched the live this morning. I couldn't remember, but it seems that there is some effort in trying to understand what's going on inside the network.
Yeah, may I just reply to that very quickly? Yeah, so I'm just going to reply to that very quickly. Yes, I know that I completely agree, and I think those are very good efforts. I am talking, but I see that as like things that need to be developed and are right now being studied and being understanding better. I will not comment on the interpretability of these things because I don't know this method, so I don't know them. But what I'm talking about is the traditional machine learning with everything that we already know. With everything you already know, if you take into account the characteristics of your input data and how this was trained and what is the domain in the parameter space where you can believe you have sufficient statistics and sufficient information to extract from this data set, those are very well established theorems already, and we can have a very good idea of where a given method will work or not based on the characteristics of the input data. But I completely agree with you that there are other things being done that we should obviously keep an eye on them.
Caroline?
Yeah, I totally agree. So I think also that maybe we have to distinguish between things that help us to better interpret and things that really help us to trust the network. Like, I mean, and this comes back to the errors that we really like, okay, we have catastrophic outliers for classification or we don't, or well, we have a good model error. I mean, in the end, it's a model error that we have if we have that many parameters in the network. So I think it's, yeah, so there's interpretation things that can really help us, and maybe also to judge if our uncertainty calibration was actually reliable or not. But in the end, we want a really reliable uncertainty calibration. And maybe a second really quick point on what Amy had said before on the or what also the others had raised partly on, well, open data, and we have to understand the code and it needs to be well documented for us to also move forward. I think we also sometimes, if you look at industry, kind of like something like Google Net or so, then, I mean, they have incredible many layers, incredibly many parameters. But then if you talk to a data scientist and they look at the data that we have, or the data that we have labeled, they actually look at it and they're like, oh my God, this is like, you have like so few data. It's like, it's tiny for them often. And then they say, okay, like this, I mean, they say, okay, don't do a 18-layer network, do like a shallower one. So we also need to be careful to just take stuff that works well in industry, because also they don't care about it, uncertainty so much. And also they have much more data usually for training than we do. So I think we need to be careful also there.
They also have actual data, not mock data. We have one universe, so unless somebody can make more actual universes, we're unfairly comparing to ourselves to them.
And they have no uncertainty in their labels. They are pretty sure that their labels are completely what they are.
Yeah, they're pretty sure that that's a cat in the photo. It's not something else,
Yeah, I think we moved a bit forward, and at the beginning where there was a lot of hype about machine learning, so we were applying somebody else's network trained to distinguish dogs and cats to our galaxies in an aerodynamical simulations. I mean, I think we moved forward a lot. So I disagree that now we are dealing with black boxes. I think we understand them more and more, and of course we need to work more on this, and we need to learn more from data scientists and people that actually work on the theory of this stuff. But I think we already moved forward a lot since we started using these methods in astrophysics. So I'm more optimistic than Garrett, for instance.
I'm not necessarily pessimistic. I was just more, yeah, we should be cautious, especially if we're, we move to a situation where we have a number of developed tools which people have accepted, and I don't know. I mean, what I'm seeing in the presentations is that people are still developing things, and then they can compare to the test, etc. We haven't seen any. I mean, so that I guess it's when you move out and actually apply it to cases where you don't know the answers. You know, is this? Yeah. How certain can we be? But there was something else. Now I forgot what I wanted to say. Okay, let somebody else speak.
I think we're drawing close to where we have to close off. Am I right?
Yeah, I mean, I'm quickly looking the program.
I mean, I could be completely wrong. If not, that's great because we can keep talking for a long time.
Yeah, well, a quarter past, we should technically stop, but we can take some time for the final words if someone else has some particular remark that want to ask to the community.
And announcements.
Yeah. Just wanted to mention also what I've noticed compared to 1 year ago, where I believe not the first, but I've seen definitely an increase of work on machine learning applied to ionization, cosmic dawn. Seems to be that it's more toward this kind of emulator in principle, where you know your target is well defined and you are more you're less uncertain on your prediction in principle. I don't know if this is a general feeling, but I think for example this meeting in particular has been a good example to see how we can speed up, say, general simulation that we use for analyzing output. I can remember just on top of my head on the first presentation of the second day. I have the program just with me, so I can. Mazipa, I think, she was proposing this accelerating reionization simulation. And this can have quite I would say, an impact on how we can do, I don't know, and imagine something like bubble size distribution analysis or stuff like that, where you can reproduce a much faster large data set that they can do than you can use for, I don't know, MCMC or stuff like that. Don't know if you have any remarks on that.
We have 2 remarks on that. Emil?
Sorry, very quickly, just my last defense. Every time that I try to understand a little bit more of the emulators, I have 2 very conflicting feelings. From the one side, I think like this is nice, but there's a high probability that it will create something that was not in my data, and then I may not recognize, or it might drive me to a path that I would not take otherwise if I was not using this emulator. And on the other hand, I think maybe this is a region of the parameter space that we just didn't look at, and we should have been looking at that. And this is what the emulator is telling us. And so, although I don't have a formed opinion about it, but I have this dual reaction to the idea of using these things in science. And I think this is very interesting. A very good, exciting outcome of this would be that if we actually found something suggested by an emulator that we didn't find in data yet, but it could encourage us to actually search that parameter space in that region for more things.
And Harold?
I just remembered what I wanted to say, which may be actually wrong, but okay, I'll just say it. So my impression also from this meeting is that we're quite good in taking methods that have been developed by others or in other contexts and applying them to our problems. So historically, astrophysics, astrophysical research has been often driving different techniques. So, for example, if you go back to the 70s, I think developing accurate methods for hydrodynamics was very much pushed by astrophysics. I think I have the feeling even this kind of Bayesian analysis, astrophysics became kind of prominent, and that led to all kinds of spin-offs, etc. I don't get the feeling that with machine learning, and maybe I'm wrong, maybe there are, but it would, in some sense, it would be good. Let's say the remark that is made that we actually have quite little data compared to the industry people, but maybe there's something there that actually we can push the machine learning field by saying, okay, we can improve things even if we have less data than typical other applications. So it's sort of a reflection. I don't know. There are probably people here who know more about these developments than I do. But yeah, I think it would be interesting if we could become leading in this field, or in some directions anyway.
I think answer, and this is one point, and then also active learning. And I know that people here have done work on this, but just to very briefly branch in. So I saw some, but sorry.
Fine. I just wanted to comment on what Gail said. Isn't that exactly what we are contributing to the industry? We are contributing how machine learning can be applied to less data. That's exactly what we're providing to others. No.
Okay, good, but yeah, we should sell it maybe as such. Yeah.
Just one comment on that regard about the interaction with industry and with computer science people. I think what we have is a huge opportunity, because when you talk with people from computer science, and especially the people who work in the theory of these things, they are always looking for problems, and we have problems they never heard about. The problem is when we are talking, when we decide to do this kind of interaction, is that the language is so different, and it takes so much effort to at least try to begin to understand what one another is talking about, that most of the times it's easier to start from scratch. But I think we get in a point in the complexity of the astronomical data and in the complexity of the machine learning models that one will not do the other from scratch. So I just wanted to put the attention a little bit in the last point, since we have to finish, that I think it's very important also to understand how do we optimize the work in the community. And I think that I completely agree with the fact that we should be, we must encourage developments in the development level, even in the theory level, to deal with the kind of data that we have. There's a lot to be done, and a lot of, Caroline mentioned active learning is just an option, but there's a lot of things that can be done with simple classifiers and not so much data, if we can actually understand and actually put the domain knowledge inside the algorithm. But that will only happen if we are able to collaborate with people who have no idea what our data is about, and explain to them how all of the caveats we have are super important and they cannot be ignored. And that's more like a sociological question, I think, than in a practical one.
I agree with you. I mean, in my limited experience, I see there is a lot of communication between, let's say, computer science that are more, let's say, oriented on the machine learning part, and astrophysics. For example, in my department in particular, there are a lot of these, what are called machine learning for science project, that correspond of very brief 1 month master project, where some student from computer science come in and basically try to learn something about the subject. At the same time, you give them with some work that you don't want to do yourself, maybe. But there is, I mean, it seemed there is some level of communication, and this can maybe lead to something positive or some new outside look, let's say. Yeah, exactly, Steve. The many grad student researcher as a powerful source of work. Yeah.
Sambit, do you have a comment?
Okay, I forgot to lower my hand, but I do have a question. I just have a general question for everyone because I want to hear your views. For the astronomy and cosmology community, what is better? Like, there are two ways in which we can use these machine learning methods. One is using many different methods to improve one thing. Like we heard many of these global signal emulators. They are trying to improve the accuracy. And then other talks where they were applying machine learning methods to different problems. So, and for us, I mean, what is exciting? So do we try to improve emulators because we think data will come soon and we can analyze them, or we try to find more problems where machine learning can be useful? I mean, it can be both. I just wanted to hear your views.
I think it depends on you, what you want to do. If you care more about the astrophysical question, or more about the challenge of building a new method, I don't know. I guess it really depends on the scope of each one. But that's my opinion.
Yeah, you get half of the babies doing one thing and the other half doing the other.
That's a good idea.
All right. Maybe since there is not a lot of time left, we're already over time actually. I wanted to take advantage of the last 10 seconds to thank Caroline, Michael, and Sambit for the really nice work they did as co-chairs of this meeting. I'm clapping on behalf of everybody.
Thank you.
Thank you also to the other SOCs actually to helping out with organizing
And thanks
the season.
to, of course, all the other SOC. Yes.
Yeah. And
all the
Stephen
amazing
Wilkins.
speakers.
Exactly, yes. And also Stephen Wilkins and
interfered.
Will. Oh, sorry, I missed a bit. I wanted to just say thank you also to Stephen Wilkinson and Will Roper for the technical support, let's say, and that was very helpful. Okay.
Yeah.
We can stop here.
Thanks to all. Yes.
Yeah.
And maybe we can pick this up and have another machine learning update at some point. That would be great.
Yeah. Thank you. Thank you all.
Thank you.
Bye. Have a
Bye,
nice
bye.
evening or day.
Bye.
Bye.